We've all seen this chart hanging on the wall in science class, right? The periodic table of elements. But what if I told you this isn't just a chart, that it's actually a map, a kind of cheat sheet, a secret code that unlocks the fundamental rules of the entire universe?
I mean, think about it. Imagine the challenge scientists were facing. How do you possibly create a master list of every single building block of matter? Everything from the air we breathe to the stars in the sky. I mean, where would you even start? It sounds kind of impossible, doesn't it?
So, to really appreciate the pure genius of this table, we've got to go back in time, back to an age of total chemical chaos.
Okay, so put yourself in the shoes of a chemist back in the 1800s. You've got dozens of these elements figured out, everything from hydrogen to uranium, but they're just a random collection of facts. There was absolutely no rhyme or reason to it, no way to see the relationships, and, this is the big one, no way to predict how a newly discovered element might behave. It was literally like having a box full of puzzle pieces with no picture on the box to guide you. A total mess.
And then our hero enters the scene, Dmitry Mendeleev. While everyone else just saw a jumbled list, he saw a pattern. He started arranging the elements he knew about by their atomic mass, and he noticed something incredible. Their properties started repeating in a regular, periodic way. But his real masterstroke of genius? He was so confident in his pattern that he actually left blank spaces in his table, predicting that new, undiscovered elements must exist to fill them. He even described what their properties would be. How gutsy is that?
And you can see here Mendeleev's early table with all those bold, predictive gaps. It eventually evolved into the modern table we use today. And guess what? He was right. But there was one final piece to the puzzle. A guy named Henry Moseley figured out that the real key wasn't atomic mass, but the atomic number. That's the number of protons. And with that one last insight, the map was finally complete.
Okay, so we've got our map. Now the question is, how do we read it? What do all these boxes and numbers actually tell us?
So at its most basic level, the table is just a grid. The horizontal rows are called periods. As you move across a period, you're just adding protons and electrons one by one. The vertical columns? Those are called groups, or sometimes families. And just like a real family, all the elements in the same group share similar traits, similar chemical personalities.
Now let's zoom in on a single square, let's say for carbon. You see its vital statistics, right? Atomic number, its symbol, its mass. But look at that little line at the bottom, the electron configuration. That little string of letters and numbers? That right there, that's the key to everything. It is the secret code that explains the entire shape of the table.
Which, brings us to the big question. Why does the periodic table have such a weird, disconnected shape? It's not a simple rectangle. Why are there these strange towers and that big valley in the middle? And what's with that floating island at the bottom?
Well, the answer is just beautiful. That shape is not an accident. It's not random at all. It is a perfect physical map of the invisible rules that tell electrons where to go inside an atom.
See, electrons don't just pile into an atom any old way. Think of it like filling up seats in a movie theater. You always take the best, lowest energy seats first. This diagram here shows that specific filling order. It's called the Aufbau principle. They fill the 1s orbital, then the 2s, then 2p, and so on. Now, it might look a little complicated, but trust me, this precise order is the whole secret.
And now, the big reveal. Look at the periodic table, but broken up into these different blocks. You've got the S block, the P block, the D block, and the F block. If you just read the table like a book from left to right, top to bottom, the blocks appear in the exact same order as that electron filling diagram we just looked at. It's amazing. The table isn't just organized by electrons. Its very shape is the electron code made visible.
Okay, so that's the why. That's why it's shaped like that. But what's the payoff? What's the point? Well, now that we understand the map's layout and its secret code, we can use it to predict an element's personality without ever even meeting it. Let's start with something simple, atomic radius. This is really just a fancy way of asking, how big is the atom? It's the distance from the very center of the atom all the way out to its most distant electron. And the periodic table shows us a beautiful, super clear trend. As you go down a group, you're adding more and more energy shells, so naturally the atoms get bigger and bigger. But, and this is the cool part, as you go across a period from left to right, the atoms actually get smaller. Why? Well, because you're adding more protons to the nucleus, which creates a stronger positive charge that pulls all those electrons in just a little bit tighter.
Okay, next up, ionization energy. I want you to think of this as an atom's grip strength. It's the amount of energy you'd need to steal one of its outermost electrons. So a really high ionization energy means the atom has a super tight grip and it does not want to let go.
So, where are the atoms with the strongest grip? Right at the top right of the table. The energy it takes to rip off an electron goes up as you move across and up. And this makes perfect sense, right? The atoms on the far right are so close to having a full outer shell, they are holding on for dear life. Meanwhile, the huge atoms at the bottom have electrons that are so far away from the center, it's way easier to just pluck one off.
And finally, we've got electronegativity. Now, if ionization energy is all about holding on to your own electrons, electronegativity is about how badly you want to steal someone else's electrons when you're forming a chemical bond. It's basically the best measure we have of an element's chemical greed.
And just like our last trend, the greediest, most electronegative elements, they all hang out in that top right corner, with fluorine being the undisputed king of greed. They are desperate for just one more electron to feel complete. And on the flip side, the most generous elements, the ones most likely to just give an electron away, they live all the way down in the bottom left.
In all these trends, they create this fundamental divide on the table: metals versus nonmetals. The metals, over on the left, are generally shiny, they're great conductors, and they have these loosely held electrons that they're pretty happy to just give away. The nonmetals, over on the right, they're often brittle, they're poor conductors, and they hold their own electrons super tight while always trying to attract more.
So, let's just put this all together. We've gone from a totally chaotic list of facts to this incredible map that encodes the secret rules of electrons. But the true power of this map is what it lets us do.
So the crucial takeaway is this: an element's location is not random. Its address on this map tells you pretty much everything you need to know. You tell me where an element lives on the table, and I can tell you roughly how big it is, how tightly it holds its electrons, how greedy it is for more, and whether it's going to act like a metal or a nonmetal. It turns chemistry from just a bunch of memorization into a beautiful science of patterns and predictions. It's the ultimate cheat sheet.
And that really brings us to a final, pretty incredible thought. What if scientists managed to create a brand new element tomorrow, let's say element 120? It might only exist for a tiny fraction of a second, but because of this map, we would already know so much about it. We'd know its probable size, its personality, its chemical family, all of that predicted before it even exists. The code is right there, just waiting for us to read it.